Last week, at the end of last week, we briefly reviewed Chapter 3 Vector Calculus. Today, we study in detail. In Chapter 3 and Chapter 4, we consider the derivatives and integrals involving the vector field. The nth order derivative of a function is defined, the first order derivative of a function is defined by fx plus h minus f of h divided by h. We take the limit h equals to 0. And if the limit exists on the left and right limit and left limit are the same, then the function is called differentiable. That function is called the derivative. If I take the differentiation once, it is first order derivative. If I do it twice, it is second order derivative. If I take the derivative by n times, then it becomes the nth order derivative. Product function we can find the derivative of product functions in this way. Suppose we have a product of f and g. The prime is the result we know is f prime g plus f g prime. In case we take the double derivative of a product function, then we can do it twice. First of all, I can take the derivative of f and g to find f prime g plus f g prime. And we take another derivative to find f double derivative g. And here, I take the derivative of g here, and I take the derivative of f in the second term. So f prime g prime appears twice. And then the second order derivative of g appears when the derivative is not applied to the f at all. A single derivative of a product function, this formula can be proved as follows. First, we substitute the argument x plus h to both f and g and subtract the value at both f and g are at x. Then to find the contribution f prime term, then we had better factor this one out. But unfortunately, this f of x and g of x plus h term does not appear in the previous result. Thus, we have to add to cancel the fictitious piece to be cancelled. So this one and this one was the original value, but this one and this one then becomes 0. Then we multiply 1 over h, the difference of the arguments. The second piece, we can factor this f out, but difference is related to g. So the first term, after multiplying 1 over h to the difference of h, we have the derivative of f. And g x plus h approaches g of x. The second piece, f is remaining the same, but g has the difference divided by h. After taking the limit h goes to 0, we find that f prime g plus fg prime. This kind of product, we can apply the same method to the triple product of functions. You take the derivative, then one by one. First one is the second one and third one. Actually, the difference is that we have replaced a single factor by its own derivative. So it's better to factor f1, f2, f3 out. And then replacement means divide by that function multiplied by the derivative of that function. So sum over I equals 1, 2, and 3. So as a result, it is just a product of a k from k equals 1 to 3. And then summation of this factor, fi prime over fi, something like that. Although this is for the product of the three functions, it can be generalized to any arbitrary product of functions. In summary, derivative of product function can be a product itself and sum of f prime over f for k equals 1 to n. If I take many derivatives of product function, then I can take the, suppose that we have nth order derivative, then it's possible to take the derivative f by n times and do not take the derivative g at all. And that it is also possible to take the nth order derivative of g and do not take the derivative of f. So these are the linear combinations of kth order derivative of f and n minus kth order derivative of g. And the problem is how to count the multiplicity of the terms. We recall that if I take the derivative of f times g twice, then we found that taking the derivative, this number 2 is solely given to the f primes. There's a list of combination is 2 factorial over 2 factorial 0 factorial. 2 factorial is for the number k, that is the number of derivatives for the k, for the f, and 0 is number of derivatives for the function g. In a similar manner, the opposite side, twice derivative twice for g is 2 factorial divided by 0 factorial times 2 factorial. So that both of them are 1. But multiplicities for the cross term is 2. The reason is that I take the derivative of f twice, but once for f, the other ones for g. So it is 2 factorial over 1 factorial over factor. That gives a factor of 2. This is the combination of nth order derivative, n factorial divided by k factorial. That is the number of f derivatives, and number of derivatives for g, that is n minus k, is a factorial in the denominator. So if we substitute n equals 2, then we reproduce this result. Let us consider the angular momentum. Orbital angular momentum L equals x cross p. And time derivative of the angular momentum can be computed as in this way. Let's see. Orbital angular momentum L equals x cross p. The cross product of x and p is a linear combination of EI hat and the ith Cartesian component of the orbital angular momentum is epsilon ijk, xj, and pk. The rotational version of the Newton's second law is this equation. Torque is the total time derivative of orbital angular momentum. So let us compute the total time derivative of orbital angular momentum. If we substitute this expression into the orbital angular momentum, we find that here we notice that the unit vectors of the Cartesian basis vectors are constant vectors. So if I take the time derivative of that unit vector, it vanishes. The Levi-Civita tensors are just either plus or minus for permutations. And if it is not permutations, that means that we have at least two repeated numbers, then those values are just 0. In any way, epsilon ijk is a pure number. Therefore, if I take the time derivative, it vanishes. The only time dependence appears in x and p. So let us factor this constant tensor and vector p's out of the derivative. And this is the derivative of two factors. So xj and pk. We can apply the derivative rule for the product function. So we can take the derivative of x first. This is the term. And we can take the derivative of pk next. Finally, we have this vector. pk is actually the k Cartesian component of linear momentum. And linear momentum is mass times velocity. It's mass times velocity. If I substitute this one here, then the first term has m factored out in front, and ei hat, epsilon ijk, xj, and xk. You find that x dot j and x dot k are symmetric under exchange of j and k. And the Levi-Civita tensor contains the vector indices j and k that is anti-symmetric. If the summation is over for two indices, one of which both of them are attached to anti-symmetric tensor and symmetric tensor simultaneously, the final result is always vanishing. So remaining non-zero pieces, the only remaining non-zero pieces, ei hat, epsilon ijk, xj, pk dot. Pk dot is the time derivative of linear momentum. That is actually the force. So this is x cross p dot. P dot is by Newton's second law of motion. It is a force. So x cross f is the torque. So next we consider the chain rule. The chain rule is a formula for computing the derivative of the composition of two or more differentiable functions. Consider a composite function. F of x is actually function capital F of x is a function f of g, and g is a function of x. This is called a composite function. So derivative of a composite function capital F of x can be computed in the following way. So capital F is taken by the differential derivative of dx, then substitute everything to find that is capital F is a small f of g of x. First, we compute the derivative of f with respect to g. You see, the argument is g instead of x. And then you take the derivative of g with respect to x. The chain rule can be expressed in terms of Leibniz formulation. This is df over dg and dg divided by dx. So this one cancels infinitesimally to find that this total derivative can be obtained. This is an example. If I take the derivative of x plus 2 squared, then let me substitute y instead of x plus 2. Then this is a function y squared. So y squared can be taken, we can take the derivative with respect to y first, and then take the y derivative with respect to x. Here, this guy is 2y, and then I have dy over dx. Because y equals x plus 2, its derivative is 1. So 2y, x plus 2 is substituted, and then dy over dx, 1 is substituted to find the final result 2x plus 2. 2 times x plus 2. Next one is a natural exponent. Natural exponent is defined in this way: 1 plus 1 over n, and its power is n. After that, we take the limit n goes to infinity. The numerical value for this natural exponent is 2.718 and so on. And this is an irrational number. One more important thing we must remember is that suppose that we have additional terms inside the parentheses that contains 1 over n squared, n cubed, and so forth. What happens? The final result is that 1 plus alpha 1 over n plus alpha 2 over n squared, and so on to the nth power, where alpha 1, alpha 2, alpha 3, all the numerators are constants. In that case, all the remaining pieces of higher orders in 1 over n squared or higher vanishes exactly in the limit n goes to infinity. And our final result is exponential e to the alpha 1. Okay, next we consider the Taylor series expansion. Taylor series expansion of exponential x, whether it is exponential function or not, as long as the a function is differentiable to all orders. The Taylor series expansion about x equals 0 is also called the Maclaurin series. And Maclaurin series is the derivative at the kth order derivative at x equals 0 multiplied by x to the kth power divided by k factorial. Actually, the exponential function has the derivatives itself. There's a nth order derivative exponential function is itself. And if I substitute x equals 0, exponential is just exactly 1. Thus, all the derivative and function itself at x equals 0 for the exponential function is actually 1. Therefore, the Taylor series expansion of this exponential function is a sum over k from 0 to infinity, x to the k over k factorial. We can make use of this Taylor series expansion method to reproduce this binomial expansion formula. So let's briefly review what we studied regarding the natural exponent. First, this is the definition of E, and we can prove this one is converging a number to a number. And if I add the pieces of higher order in n squared, n cubed, and so on, as long as these numerators are finite numbers, in the limit n goes to infinity, these contribution all vanishes. Only the leading piece survives as a natural exponent. In addition, if I have some number in the numerator of 1 over n, then I can rewrite this one as x over n and power as n over x. They are reciprocal. But because I have divided by x, I have to multiply it by x to that power. I can take the same limit and as n goes to infinity, so that I can factor this out as n goes to infinity. This one is just n prime, something like that. 1 plus 1 over n to the nth power. In the limit n goes to infinity, this x power is factored out. Therefore, because this inside is constant natural exponent e, the final result is this one is exponential x. We can make use of this relation to find that the derivative of exponential x is the same as itself. In such a manner, we find that first of the derivative exponential function of the exponential, and if I have additional parameter alpha in the exponential function, then chain rule can be used to find that the derivative of exponential ax is a times exponential ax. In this way, the nth order derivative of exponential function is exponential itself. So, what happens to this term? If I take this function to be f of x, I can take the derivative to find the binomial expansion. Derivative of x to the n is n x to the n minus 1. Double derivative of x to the n is n minus 1 x n minus 2. Then I can replace x with 1 plus x and replace n by alpha. Then I would get this alpha 1 plus x alpha minus 1, double derivative alpha minus 1 plus x to the alpha minus 2, and so on. And then we can take the Taylor series expansion about x equals 0. At x equals 0, this 1 plus x all becomes 1, and it is independent of power. Therefore, I can substitute these coefficients all together into the formula for the Taylor series expansion. Then, first order piece has a factor of alpha, second order piece has the factor of alpha minus 1, and k factorial appears in the denominators. Therefore, binomial expansion can always simply expressed in the limit as long as this absolute value is less than 1. This expansion, this Taylor series expansion approaches the original value 1 plus x to the alpha. Okay. This exponential function and the natural exponent, you must master these relations. Okay, that's it. Let us continue to study exponential, and we studied the natural exponent and the exponential function. Today, we also consider the case that a matrix, an operator, is being exponentiated. We call that the Taylor series expansion is as shown here. Taylor series expansion, the Maclaurin series, that is the Taylor series expansion about x equals 0. The shifted amount is a. Okay, this is the sum of nth order, kth order derivatives multiplied by a's kth power divided by k factorial. Actually, this is the kth order derivative, so we apply the kth order derivative and multiply a to the kth power. So this is the same as this. And after taking the derivative, we substitute x equals to 0. Actually, a is a constant parameter, so the derivative of a with respect to x vanishes. Therefore, this one is exactly the same as a times dx to the kth power. We find that 1 over k factorial, something with k power, is actually the exponential. So we put this operator a and x derivative, exponentiate it, and apply this operator, composite operator, to f of x, and then substitute x equals to 0. Then we will find that the shifted value of f of x from 0 by a, that is f of a. So in summary, f of a is actually the same as f of a plus 0. So we expand this f of x about x equals 0 by a shifted amount a. That is the value of kth order derivative at x equals 0 multiplied by a to the kth power and divided by k factorial. We recall that this one is a to the kth power, and the kth order derivative can be combined into single one with the kth power. And then this here, if I take the derivative by a with respect to x, it vanishes. Therefore, this operator square is a dx, and something it is applied to a function. And because x dx derivative commutes with a passes to the left to make a square. In a similar manner, for any non-negative integer n, we have this a to the nth power derivative by n times is just a times derivative by n times. All right, so this is a kind of exponential. So we exponentiate this operator, apply to that operator to f of x, and substitute x equals 0. So that is f of a when it is expanded from x equals 0. What happens if I substitute x in here? Then this becomes x plus a, and operator applied to the f of x, and do not substitute x equals 0. So this is f of a, f of x plus a. what happens if I replace the sign of a by minus a? So f of x minus a is actually this one. Okay. Suppose that the graph of f of x is like that, then f of x minus a is the same as the f of x, except that the whole amount of the whole graph is translated by plus a. Then this function is x of x minus a. We remember the momentum operator P in one dimension in quantum mechanics is h over I dxd. We remember psi of x, suppose the psi of x is a wave function. Then if I translate this particle by a, we'll find that this is psi x minus a. And as we have derived, this one is a derivative exponentiated and applied to function of f. This is psi of x in this case. Alright, so this is minus I h bar dxd. So here we substitute a equals IH bar. Then our answer is correct. This guy is the same as this. And I can replace this one with the momentum operator. Let me just put subscript x to denote this direction of x. So psi of x. So p of x is exponentiated. So we say that this is a momentum operator. Linear momentum operator. This is generator. Spatial translation. We can extend this method to three-dimensional cases. Suppose that we want to find the shifted value of this is a f is a function of x, y, and z. If I want to shift this function from the original f of x, y, z, then what I can get is this is shifting x by minus a, right? And then y minus b indicates that this function can be obtained by shifting y by minus b. That is this. And then z minus c, this can be obtained by shifting z by minus c. All right? We have f, x, y, z. Then we have operator We remember that if I want to do this calculation, it's better to write, make use of the partial derivative instead of total derivative, because it is a function, f is a function of multivariable x, y, and z. So the correct way of writing this operator is so if I apply this one to f, y, z, then this one is f x minus a, y minus b, and z minus c. All right. Just like what we have done with the wave function, suppose that we have a wave function of a particle at x. I want to move this particle by vector a as a displacement. Then I need to apply this amount, psi x minus a equals e to the minus a psi of x vector. And actually this is e to the minus that is here a, b, and c. Let me call this one a, b, c is just a vector a. This is a1, p1 operator. This is not a unit vector but an operator. As you know, they commute, and this one commutes, and if I attach h bar over I squared to this, you will find that pi at pj commute. If they commute, these three exponent combines. So we can apply the law of exponent just like the numbers. And this is scalar product. All right. So quantum mechanical wave function for a particle, for a state. If we want to shift the wave function by a, then what we have to do is exponential of this minus I over h bar a dot p. Once we apply this one, then you will find that the particle, so wave function, is shifted by a finite amount. So exponential function is quite useful. This kind of explanation can be applied to the matrix. And for example, Taylor series expansion can be made for the matrix exponential of matrix. It is because matrix A, when I multiply a matrix, the number of columns of former one and number of rows of latter one must match to have their product can be defined. So in the case of square matrix, the number of columns is always the same as number of rows. So I can always define the square of a square matrix and cube of a square matrix. And in a similar manner, I can define a to the nth power. Okay, so just like what we have done for the exponentiated operator, but just like derivatives, any operator can be, as long as it is defined, the kth power of an operator can be defined, then we can sum them up by multiplying 1 over k factorial and sum them everything up, then this one is just the exponential. So let us consider the case of matrix exponentiation of matrix exponentiation. The simplest case is the rotation matrix R. This rotation matrix R is for the two-dimensional Euclidean space, and rotation is made about the z-axis and by a finite angle theta. We recall that the components x1 and x2 is transformed under this transformation, this rotational transformation, as a cosine theta, sine theta, minus sine theta, and cosine theta. This rotational matrix is commutative only if the axis of rotation is kept the same. In general, the rotation about, for example, about x-axis and then rotate about the y-axis and z-axis, then they do not commute at all. However, if we keep rotating in the same along the same direction, then the rotation operator or rotation matrix, they commute. This is an example. A simple example is a multiplication of two complex numbers that is equivalent to the two-dimensional Euclidean space. If I multiply two complex numbers, the unit modular, the magnitude of C is 1. Unit modular complex number is always expressed as the cosine plus I sine. So this exponential I alpha and exponential I beta are multiplied to find that the arguments are combined together. If I multiply two rotation matrix, let us rotate about the z-axis by theta 1 first and theta 2 next. If I multiply two matrices, then the 1 element will be cosine minus sine. So cos, sine, that means cosine theta 1 plus theta 2. 1, 2 element will be the 2, 1 element. Sine theta 2, cosine theta 1, cosine theta 2, sine theta 1. They are added. That means sine theta 1 plus theta 2. 1, 2 element of this product matrix is cosine theta 2 minus sine theta 1 minus theta 2 cosine theta 1. So sine, cosine, cosine, sine. But both of them has a negative sign in front. Therefore, we have minus sine theta 1 plus theta 2. So two elements will be fine this way. Sine theta 2, sine theta 2. Negative sign. Cosine theta 2, cosine theta 1. So cosine, cosine, positive sign, and sine, sine, negative sign. So there is a cosine theta 1 plus theta 2. You can see this theta 1 plus theta 2. All expressions are theta 1 plus theta 2. So theta 1 and theta 2, if we exchange theta 1 and theta 2, this result is always the same. Therefore, this one is our theta. First, we rotate by a theta 1 and then rotate by theta 2. The result is just a single rotation with theta 1 plus theta 2. And because this matrix is symmetric on the exchange of theta 1 and theta 2, it is exactly the same as rotate by an angle of theta 2 first, and then rotate by an angle of theta 1 next. In a similar manner, if I rotate many times r theta 1, r theta 2, and r theta n, then this is a single rotation by theta 1, theta 2, and theta n. What happens if all the angles are the same as the theta? It is r n theta, and this is r theta to the n. What happens if I slice this one into n pieces, n equal pieces? Then r theta equals r theta over n to the nth power. All right? So this is an exact relation. So r theta over n equals cosine theta over n sine theta over n minus sine theta over n cosine theta over n. We recall that sine theta was the theta minus 3 factorial theta cubed cosine theta 1. Alright, so let us keep, we can substitute theta over n, theta over n, theta over n. It means n cubed, n squared, something like that. Then, equals 1 minus 2n squared theta squared plus, they are all theta minus theta we can divide this one into all the zero term. That's independent of n, independent of theta. It is just one. Linear piece. Linear piece is here. Theta over n, theta over n. Plus theta over n minus 1, 1. And then higher order piece, what about this guy contain theta square over n square, theta cube n cube, and so forth. All right, so let us consider the previous result. R theta is just R theta over n repeated by n times. Actually, this one is 2 by 2 identity matrix. This one is identity matrix plus theta over n. We remember that exponential, as we take the limit n goes to infinity, this is exact, but if we take the limit n goes to infinity, that all the contributions of 1 over n squared or higher vanishes. And we record that 1 plus x over n to the n, limit n goes to infinity, this exponential x. In a similar manner, n goes to infinity, identity operator, 1 over n, matrix A to the nth power. This one is just exponential matrix A. Therefore, our result becomes e to the theta. But we remember that this one is cosine theta, sine theta, and minus sine theta, cosine theta. This is parameter, angle, real parameter. This is called the generator. Generator O2. Actually, this is SO2. O2 is rotation orthogonal. They are orthogonal, but as well as they are orthogonal, the determinant of R is cosine squared plus sine squared. So it is always a plus 1 because determinant is 1. This is a continuous rotation. So continue as a continuous group, all of the continuous group can be exponentiated with a real parameter and a matrix. And this matrix has a special property, traceless, anti-symmetric. Traceless and anti-symmetric. But sometimes we can use this one as e to the I theta minus I theta and multiplied by I. They are the same. E to the minus I. If I insert this one into matrix, this is Pauli sigma matrix I2. And this is traceless and Hermitian. Next, we consider the summation of that exponentiated matrix. This can be computed by making use of the relation shown in here. All right, matrix A has a vanishing diagonal elements. It is off diagonal only. So 0, minus 1, 1, 0. Let us first square this matrix. If I square this matrix, the final result is minus identity. Let's see. One element will be this one multiplied by this. So I have minus 1 in here. 2 element is 0. 1 element is 0. 2 element is minus 1. So I have an overall negative sign, and it is proportional to the identity. Because A squared is minus identity matrix, if I square this matrix, then it becomes a plus, and so on. So even powers of this matrix A is either identity matrix or minus I identity matrix. Minus identity matrix. So minus identity matrix and power. So this one is always identity, so I have a minus n here. And if I have odd powers of A, then it becomes a A to the 2n is minus n, and then multiplied by A matrix A. So power minus n to the nth power and identity times A. The final result is this. So let me make use of this relation to find the sum. Exponential beta A equals sum over k, 0 to infinity, k factorial ak, where k A equals minus 1, 1, 0. Okay. I can divide this one into two pieces, even and odd. Okay. This one is minus 1, k. Identity. And this is minus 1, k. And A. And actually this is number and they are factored. So we have identity and this one. This one is actually cosine theta. And this one is a sine theta. Now bring this definition here. We have cosine theta, 0, 0, plus 0, minus sine theta, 0. If I add these two up, I have cosine theta, minus sine theta, sine theta. Alright, so our matrix exponential can be summed after expanding power series, just like the Taylor series expansion of exponential number. we can simply obtain the finite result. And this is our starting point, this rotation matrix in 2 dimensions. So, in summary, this is as a finite rotation. The rotation on the 2-dimensional Euclidean space can be expressed in terms of an exponential of traceless anti-symmetry matrix. And we were able to sum this exponential of matrix as the cosine, sine, minus sine, cosine. That is the rotation matrix in 2 dimensions. Next, we consider vector differentiation. A field is a function that depends on the positions. The position vector x has 3 components, x1, x2, and x3. And if the final result, the value of the function is a scalar, then we would say it is a scalar field. Field is just a function of spatial position, vector x, polar vector x. Next, we consider the vector field. Vector field is the same as the scalar field, except that its value is a 3-dimensional vector. Still, its argument is x, so the vector field has a different vector value at each position, depending on the position. Under rotation, scalar field is invariant. So, while the scalar field is invariant under rotation, a vector field can rotate about in a covariant way, where Rij is the Ij element of rotation matrix in 3 dimensions. All right, next we study the parity. Parity is an operation that transforms a polar displacement vector as x2 x prime, that x prime is just minus x. It is the transformation, flipping the vector, keeping the tail at the origin, and transform the head on the opposite side. We classify the scalar and vector field used to 2 pieces each. First of all, V is a vector if it transforms under rotation with the covariant definition of multiplying matrix R. However, displacement vector x is a vector that has a parity negative. So, V is a vector that transforms like R x prime. The value is something like that. It's just a displacement, polar displacement vector. But any vector follow the same rotational form. However, this rotation can also be made even for an axial vector. That is actually the cross product of 2 vectors. The difference is that they have different parity. A vector, just like polar vector, polar displacement vector, they are parity odd. Okay, but axial vector, sometimes it is called the pseudo vector. It has the same rotational property as a usual vector. However, if we flip the sign of a polar vector inside, still the sign of the resultant vector does not change the sign. That is the example of a pseudo vector or axial vector. For example, displacement. Displacement is a vector. It has an odd parity. It has the rotational property like that. What happens to the velocity? Velocity, numerator of the velocity is the difference of polar vector. So that is a polar vector. Difference is still polar vector. So rotate follows the rotation transform and flips the sign when we apply the parity. What happens to the t? T is a scalar that does not change under parity transformation. Therefore, the parity of x and parity of v is the same. And m is also scalar. And p is just velocity times the scalar. So all three objects, x, p, and v, follows the same, exactly the same rotational transformation rule. And they have the same parity transformation rule. They flip the sign on the parity. Next, we consider the orbital angular momentum. Orbital angular momentum is a cross product of x and p. Product of x and p. So parity x cross p. So on the parity, x is replaced with minus x, p is replaced with minus p. So if I substitute both of them, because odd powers appears twice, the angular momentum L does not have a negative parity. It has a parity even. So orbital angular momentum follows the same rotational rule. However, its parity structure is opposite. Therefore, L is not a vector, but an axial vector. A scalar field is invariant under rotation, and it is also invariant under parity. For example, x squared is a scalar. If I apply parity, this scalar does not transform at all under rotation. And then, if I apply parity, x becomes minus x. But because x appears twice, x squared does not flip the sign. Therefore, this scalar is parity even. Furthermore, any function of r, that is the magnitude of this vector, is also a scalar. For example, electrostatic potential Q over R up to over a vector 1 over 4 pi epsilon 0 in the vacuum. It is a scalar. It does not transform either under rotation. In addition, it does not transform at all under parity. So scalar is invariant under both rotation and parity. Last one is the pseudoscalar. Pseudoscalar is invariant under rotation just like scalar. However, if we flip the sign, it does flip the sign, unlike the normal scalar. Suppose that we can construct a scalar object just like a cross b dot C. This is a triple scalar product of a vector and of three vectors. You know, vectors follow the rotational transformation, and three vectors are multiplied. If we flip the sign, A, B, C, all of them flip the sign. But because there are three vectors, I have -1 Q. That means negative sign over. Unlike the scalar that does not change any sign under parity transformation, pseudo-scalar flip the sign. Next, we consider the gradient operator. A gradient operator can be applied to many cases, but in case it is applied to a scalar function, we obtain a vector field. The gradient of phi is defined in such a way that linear combination of three vectors, and each Cartesian component of that gradient phi is the partial derivative of the scalar field with respect to that coordinate. So E1 hat has the component round phi over x1. E2 hat has the component round phi over round x2. E3 hat has the round phi over round x3. If I make use of Einstein's summation convention, then the gradient phi is expressed in such a way. Let us compute a gradient of some simple scalar function. For example, I can introduce radius r, that is square root of a square of a vector x. If I want to compute the gradient of a scalar, I have to take the partial derivative of that scalar with respect to each coordinate. First of all, I take the derivative with respect to x1. If I take the derivative of r with respect to x1, then I can apply the chain rule. This is just r. This is a square root of r squared, something like that, x squared. So square root derivative is 1 over 2 square root inside this same. And then applying the chain rule, I take the derivative of this argument inside the square root, that is x1 squared plus x2 squared plus x3 squared. The partial derivative of this with respect to x1 is 2 times x1. So numerator is that factor. So 2 cancel, and I end up with x1 over r. In general, this one can also be applied to compute the ith component, ith Cartesian component, and ith Cartesian component partial derivative is xi over r. As a result, what I obtain for the gradient of r is the sum of Cartesian components, whose components is round r over xi. That is actually xi over r, just like here. If I combine these two, xi, ei, hat, that means just original vector x. So x vector divided by r. And r is the magnitude of x. Therefore, er, this xr, x divided by its magnitude is a unit vector along the x vector. That is er hat. In general, I can apply this method to arbitrary function of r. Then again, I can apply the chain rule. If I apply the chain rule, the partial derivative with respect to xi is just derivative of f with respect to r, and then partial derivative of r with respect to xi. That means just xi over r. That is, if I combine these two, I obtain e. This one is combined to have er hat and df over dr. That's it for today.